Hello friends. You know what's great about being at home? You can bring food into the classroom. Oh yeah. Oh, fantastic. I really wish you were all here. I love eating in front of people. Okay, physics. This lesson is a direct follow-on from the last lesson that showed you how to calculate total resistances in series and in parallel. Now this monstrous question actually appears in your textbook. It's on page 132 and it says, it just gives you that diagram, not as beautifully as I've done it, and it says find the potential difference across every resistor and find the current through every resistor. So this is going to take a while. This is why this video is only one question. Now, this is the ammunition we have to use over here. These are all the formulas, all the rules that we can use to sort this out. And a good thing about this is that it sounds like an enormous problem, but it's actually just a lot of small ones. Right? So we've got V equals IR, power equals VI. We might not use that. They didn't ask us for power, but it's there. And how to add up resistances in combination, right? That's in series, that's in parallel. We're probably going to use certainly those three, maybe that one as well. Now we're starting the beginning, like I said in the last video, the first thing you often do, no matter what they ask in these circuit analysis questions, is you find the total current, because they nearly always give you the total voltage, but sometimes they don't give you any current, and the only current you can find first is the one that comes out of the battery, because that's the only V that you've got, right? Keep in mind, V equals IR, the V and the I and the R have to be for the same parts of the circuit. We've only got the voltage for the whole circuit, so we're going to find the current for the whole circuit. We don't have a choice. And to do that, of course, we've got to find the resistance of the whole circuit. So we need to first find out what all of this resistance adds up to. So one step at a time, we're going to do that. We're first going to figure out what these parallel sections add up to and then change them to one resistor. I'm going to show you how to do that right now. I'm just going to sort this across. Okay, so the parallel formula, 1 over the total equals 1 over 1 plus 1 over the next one. We're going to do that for this right now. Okay, now you notice that I've labeled a few things. This is an A and a B and a C and a D there, just so that I can communicate with the person who's marking my test. And I can say that right now I'm finding resistance from A to B. Tell yourself as much as anyone else what the hell you're doing. All right. So it's parallel. So it's 1 on the total is going to equal 1 on 5, because that's a 5 ohm, and plus 1 on 10. Therefore, RT equals, now that equals 3/10. Right? So you have to flip that answer. It's 10 over 3. 10 divided by 3 is 3.33. If you, when in doubt, get a calculator, right? I just did that one on my head. So what that says is that you could chop this whole thing out and just replace it with a straight line and one 3.33 ohm resistor, and the circuit would be the same. It wouldn't make any difference at all, right? The current would be the same, the total voltage and all that sort of stuff. Nothing would change, right? Because all of that just adds up to a resistance of 3.33 ohms. We have to do this as well for this one. So this is what's next. Okay, bear with me. Resistance from C to D. Same formula. Spell it out. 1 on R total equals 1 on 50 plus 1 on 25 plus 1 on 100. And I forgive you if you haven't done this in your head. I'm not going to either. Actually, I am. That's 7/100ths. Therefore, flipping that, it's 100 divided by 7. And everyone knows that 100 divided by 7 is 14.28. So that's 14.28 ohms. So again, instead of having all this schmozzle here, you could just replace that whole deal from C to D with one 14.28 ohm resistor. So now we're in a position to find the total resistance of the whole thing. So total resistance of circuit. Now that we know that all of that is just 3.33 and all of that is just 14.28, we can pretend that this whole thing is that plus that plus that plus that in series, because they are. right? Electrons have to go through this, they have to go through the 3.33, they have to go through this one, and they have to go through the 14.28. So that's series. That's like this. Right? So we can just add those four resistances up, and that's the total resistance of the entire circuit. Okay, so the total is 20 plus 3.33 for this bit, plus 30 plus 14.28, which equals, of course, 67.51 ohms. Okay, so the total resistance of that circuit, all of the difficulty that the electrons have going through there, is a total of 67.51 ohms. Right. Now we can find the total current finally, because using the V equals IR, we've now got the V, we already had that, and we've now got the R for the total circuit. Now we can find how much current is actually coming out of this thing. Let's do it. And again, say what you're doing. Current in circuit. Just got to center this a bit. There you go. I equals V on R. V equals IR rejuggled. Total voltage 100. Total resistance 67.51. I'm just going to pause this and calculate that. There's no way I'm doing that, mate. Got it. 1.48. So 1.48 amps comes out of here. So we instantly know the current in here. This is going to get 1.48 amps because if it's coming out there, there's nowhere else for it to go. We don't know how it splits up into this just yet. We'll figure that out in a minute. I'll show you how. Right. We do know that it gets back together and becomes 1.48 amps again. So this has got 1.48 amps going through it. And again, we don't quite know how they split for this. So I've done some of it. Excuse me. Because we know I and R for these, we can also get the V for this. We can do V equals IR and find the other thing they asked, which was the potential difference across each of these resistors. So right now we can just go, I could set it up all nicely down here, but I'm just going to do it next to it on the diagram, right? So V equals IR. And again, the V, the I, and the R have to be for the same area. Right, now I know that both of those are for here, so I can get the voltage across here. Right? 30 times 1.48, which equals, and I'll find out what that is in a minute. I'll pause it in a second. And over here, same deal. 20 times 1.48, and we'll get the answer to that now. Okay, here's how to attack these bits. You need to treat this as an entire system, okay? So instead of just looking at that wire or that wire, I'm looking at that whole thing. And we already know a fair bit about this. We know that the current through all of it is 1.48. And we know that the resistance of all of it, we calculated that before, is 3.33. And so if we've got the current from A to B and we've got the resistance from A to B, we can find the voltage across it. So V equals IR equals those two multiplied together. Excuse me. Let's see, 1.48 times 3.33, which equals 4.93 volts. So from there to there, 4.93 joules per coulomb of energy is lost. Right? Over here, same deal. We know the totals here. We know the total resistance is 14.28. Did that before, right? R is 14.28. We know the total current through it is 1.48. We don't know how it splits up, but we know that a total of 1.48 goes through the whole shebang. So again, we can find the voltage across there. Sorry, I've been teaching year 12s as well today. They're all on velocity. Pardon me. Multiply those two together and you end up getting 21.13 volts. Now, if we've done this correctly, then all of those voltage drops should add up to 100, right? Because the thing had 100 to give. And sure enough, if you add up that, plus that, plus that, plus that. Pause and do it if you want to. Trust me, that's going to add up to 100 or very close. If it's out, it's going to be out by a tiny bit, and that's just because of how we've rounded things off. Okay, the final thing is to figure out how much current goes through each one of these. Right? Now to do that, again, you have to look at what else do you have for each one of these. Let's just take this 5 ohm one here. We already know the voltage across that, because the voltage across A to B, keep in mind, this is true about all parallel sections of circuits. If the voltage from A to B is, 4.93 volts, then the voltage across it that way is 4.93 and the voltage across that way is 4.93, all right? The voltage across each one of these resistors is going to be equal. It's going to be 21.13 each, all right? We'll get to that in a second. So V for this is 4.93. R for this, of course, is 5. And you can again use V equals IR and find the current through here. So I equals V divided by R, which is 4.93 divided by 5, just a little bit less than 1. Right? I'm going to grab a calculator. Yep, 0.986 amps. Now, by the way, this means you don't have to do this for that, because you know that 1.48 amps is coming in here. And now you know that 0.986 of them went there, so the rest had to go this way, right? All of the current that comes into point A has to be accounted for going out of it. So you don't have to go through all that V equals IR rigmarole again for the other one, right? You can just add them up. You can just go 1.48 amps minus 0.986 equals, and that's the current there, right? So what I want you guys to do, I've done 90% of this for you guys right now. So you can sort of freeze this frame and have a look at all that. What I want you to do is figure out what is the current through the 10 ohm resistor and try to figure out all of the currents through here. All right, have a go. Bye-bye.